Okay, hello everybody. My name is Mariana. I'm from University of São Paulo in São Carlos, and I will present to you guys my work entitled A Key Exposure Model for Rumor Spreading on Networks. First of all, I wanted to let you guys know that this is a work in progress in its really early stages, and that's why I was thinking about presenting a poster, but I was strongly encouraged to present a talk, so I will share to you guys a little bit of my model. First of all, why model rumors? Well, a rumor is an information that propagates through social networks and probably often lacks confirmative stuff. And we started model rumors by epidemic theory because they are also a comparativity model. And the real world impact of rumors are the biggest because, as you guys know, a well-constructed rumor can be a big, how can I say, a big bomb to some things, can influence elections, final markets, public trust, and can shape our reality. No, this isn't working. So I will pass to this really quick because Guilherme already told us a glimpse of Mac-Thompson model, but it is the classical model of rumor propagation, was introduced in 1973 by Mike and Thompson, and it has three exclusive mutual states: ignorant, spreader, and stifler. Well, the transitions are modeled like this with contact, and we have this propagation rate, which is lambda, and the annihilation rate that is alpha. And it's important to mention that this is a continuous time Markov chain, and which the transitions are modeled by Poisson process, which means that the system evolves randomly over time, and the next state in the future only depends on the present state. So you don't have to deal with the past history. And in practice, we want to say that each pairwise interactions will occur at a random time, but in a well-defined average frequency. And I want to remember you guys too that this is a closed system, which means that the summarize of the states are equals to 1 always. Well, so if we have this classical model, why to try to present a new one? For me, the strongest limitation of the Mac-Thompson model is that it assumes that one contact with the spreader it's sufficient for you to propagate the rumor. And I don't know about you guys, but for me, some people need more exposure to certain rumors to start spreading. Like, for example, my grandma, when she receives news from her phone, from a gossip from a neighborhood, anyway, if she finds interesting, she will propagate instantly without checking any fonts. But as you know, we normally have to check or to heard the rumor a little bit more to start propagation. Well, to introduce this model, we have a threshold to the information to propagate, which means we have this reinforcement rule where an ignorant have to heard the rumor at least 4 times to start spreading, and which this we have the cumulative exposure. And this model can be a little more realistic at the time basis contacts. I was inspired to do this model by a paper that had modeled this for complete graphs, which is the role of multiple repetitions in the size of a rumor. And I will show you guys a little bit about the transitions. So, as I told you, an ignorant only becomes a spreader after K exposure, and this can capture a little more complex contagion that not all ideas will spread instantly in our system. And the transitions occurs a little bit similar to Mach-Thompson, but we will introduce a new state, which is the I-aware, where an ignorant have a aware state that will be counting until k, and then when it transpasses the threshold, it will propagate. Well, we have the lambda, which is the propagation rate, and alpha, which is the annihilation rate. Well, when I told you guys this was a work in progress, I meant a work in progress toward having results, so I don't have much results to show you guys yet. But what I did was use some networks, Ardos Reni and Barbaz Albert, to study the effect of the model in the structure of different networks, as in homogeneous structure and heterogeneous structure. And we fixed the degree to make sure that only the structure will be influencing in the propagation. And the goal is to analyze how the threshold will influence the final spread. And we variate both the threshold K and the contact rate. Well, these are the curves that I got, which can gives us some messages. The first message is, as we vary the K, we have the curve shifting to the right, which can mean that as we increase the threshold of propagation, you have to have a bigger rate to bigger lambda to propagate the rumor. Also, we can see that the structure of the network influences even more when you start increasing K, which means that in the heterogeneous network, the rumor have a little more difficult to spread as you increase the rate K. And also, this numerical experience suggests a continuous phase transition, which means it's a second order phase transition. And we can see this by how the curves are like going like this. So to summarize to you guys, the impact of the propagation dynamics were the K-linear, which was increasing the threshold systematically, shifting the curves to the right. We have the influence of the network, the structure of the network, when the dynamics flow, the heterogeneous difficulty dynamics to propagate. And we also have the suggestions of a second order phase transition. And as I told you guys, this is a really early stages work. So if you guys have some ideas, some thoughts, some feedbacks, you could give to me, and I would appreciate it a lot. So as I told you, this was the work that influenced my model, and I want to thank you guys for your attention.
Thank you very much for sharing your preliminary work. And so, are there any questions? Apparently, there are no questions on your talk, so thank you again, and let's clap Mariana again.